In this video, we're going to use Maclaurin series to help us find an antiderivative to e to the minus x squared. This is going to come in the form of a power series representation. So basically what we're going to do is try to use Maclaurin series to compute the integral of e to the minus x squared. And as we've seen earlier this semester, there's no known antiderivative to e to the minus x squared in terms of functions we know things about, like sines, cosines, polynomials, logarithms, things like that. So let's use power series or Maclaurin series to help us out. So here's the main idea of what we're going to do. We're going to first find the Maclaurin series for e to the minus x squared. And we're going to do this using Maclaurin series we know something about. Once we have that Maclaurin series, then we're going to go ahead and integrate it. And as we've seen earlier, whenever we integrate a power series, it's really going to turn into an antiderivative power rule problem for us. All right, let's go ahead and get started. So the first thing we're going to do, let's find a Maclaurin series for e to the minus x squared. And whenever we're doing this, we always start off with a power series or Maclaurin series that we know something about. In this case, the exponential function. So e to the x has a Maclaurin series in the following form: the infinite series from n equals 0 to infinity of x to the n all over n factorial. And as we've done previously with power series, the way in which we can use these power series we know is we can think about writing parentheses around each variable x on both sides. And once we have those parentheses in place, we can come across and just erase that variable x. The idea being, whatever we put into the parentheses on the left-hand side in the exponential, we just put on the right-hand side inside the parentheses as well. This is our composition of functions idea, or basically what we've been calling stencils. So in terms of the function that we're looking at, e to the minus x squared, what this suggests is inside of those parentheses, we want to put a minus x squared. So what we have is e to the minus x squared on the left-hand side then. Again, in the parentheses is the entire minus x squared. So on the right-hand side, what we have is the series from n equals 0 to infinity of quantity minus x squared being raised to the n all over n factorial. So we can do a little bit of algebra here, because inside of those parentheses, we really have the product of functions. We have a minus 1 times an x squared. Both of their product is being raised to the n, so we can think about it as each individual factor being raised to the n, and then multiplying those things together. So we can rewrite this as the infinite series, n equals 0 to infinity, of a minus 1 raised to the n times an x squared raised to the n. And all of that is over n factorial. However, since we still have an x squared being raised to the nth power, our variable x is being raised to the second power, which is raised to the n, we can multiply those powers together. So we could take this one step further if we wanted to, and we can rewrite this series from n equals 0 to infinity of minus 1 to the n times x to the 2n all over n factorial. So now we have a power series representation or Maclaurin series representation of the function e to the minus x squared. So the second thing we want to do is go ahead and integrate both sides. So if we go ahead and integrate both sides, we have the e to the minus x squared. We have what it's equal to in terms of its Maclaurin series, minus 1 to the n times x to the 2n all over n factorial. And we're going to go ahead and integrate both sides of this equation, and integrating both sides with respect to the variable x. Now this left-hand side, this is basically what we're trying to figure out. Again, there's no known antiderivative for e to the minus x squared in terms of elementary functions that we know, sines, cosines, exponentials, logarithms, polynomials, things like that. So the only way we're actually going to be finding an antiderivative representation is using power series. So let's go ahead and integrate what's on the right-hand side. And again, when we're integrating, in this case with respect to the variable x, all the integral cares about are the terms with x's attached, which inside this integral is really just the x to the 2n. So we can rewrite this as that integral really kind of just passing by everything that doesn't have an x attached to it. So we have this as the sum from n equals 0 to infinity, a minus 1 to the n, all over n factorial. And then we have the integral now of the x terms, the x to the 2n, that we're integrating with respect to x. So let's go ahead and do that antiderivative. Well, we're taking the antiderivative here is of x, a variable, raised to a power. So we just get to do the antiderivative power rule. So we'll take that 2n and we'll increase it by 1 and then divide by that 2n plus 1 as well. So we'll have x now raised to the 2n plus 1 power, again, adding 1 onto that power that was there, and then dividing by that same power plus 1 as well. And since we just did an indefinite integral, we would add c. So what's on this right-hand side now? This is our antiderivative for e to the minus x squared. So we just found this relationship that the indefinite integral of e to the minus x squared dx is equal to that power series on the right-hand side. So knowing something about the exponential functions Maclaurin series or power series can help us find antiderivatives to exponentials that have no known antiderivative in terms of elementary functions.